I'm Ben-Yaakov. This presentation is entitled Losses of Power Inductors in PWM Converters. This is their revised version. There is a disclaimer here that the components and design tools that are shown in this presentation are for educational purposes only, and there is no recommendation or endorsement implied. Now, this is the revised version of a previously posted video, and the revision includes correction of some errors, primarily technical errors, as well as addition of new material related to inductor modeling. I'd like to thank Just Paul and some other viewers of the original video that pointed out errors in the original version. So in this presentation, I'm going to talk briefly about inductors and PWM converters, and then talk about the reasons for losses in power inductors, winding losses, DC or AC, core losses, talk about datasheets, information we can find in datasheets of commercial inductors, and then simulation tools that manufacturers are now offering for looking at the losses. So here is a simple, basic buck converter. It's a synchronous converter, two switches. Here is the inductor, output capacitor, and this represents the load. And the point is that we do need an inductor for proper operation of a PWM topology. You can look at this inductor here like a filter that is filtering out the pulses that we have here while these are toggling, and to provide a DC at the output. Traditionally, the power dissipation and temperature rise of inductors were calculated based on the DC current and the DC resistance. So this is the power which causes the increase in the temperature of the device. We know, however, that things are not that simple. Here I'm showing a run of a body 100 of Omicron Lab. This is a network analyzer. I'm looking at a commercial inductor. This is the inductance as a function of frequency, and it's pretty much constant up to the resonant region, which we are not interested here in this presentation. And more importantly is the fact that the resistive part of the winding is increasing with frequency at a given point. This is due to proximity and skin effect. So that it starts at 20 milliohms, but then as the frequency goes up, it goes up tremendously. And as you can see, at 100 kilohertz, it's already a fraction of an ohm. And then at 1 megahertz, it's really very high. So the resistance of the wire is not constant. And this is something that, of course, we would have to take into account when talking about losses of an inductor. So if we talk about the conduction losses, that is the winding losses, we do have two parts. We have the DC part. This will be the average squared times the DC part, plus the AC part times the AC resistance of the winding. Now, this is a big question here. And obviously, with a commercial device, we cannot tell what is our AC. We have to rely on information that the manufacturer is providing. So what about core losses? Now we know that core losses, here shown is a typical chart that you'll get from many manufacturers for a given ferromagnetic material, in this case a 3F3 of Ferrox cube. It is a function, the losses in milliwatt per volume are a function of the frequency. Here's the frequency, and they be the AC component of the magnetic flux density. So these are the losses which are not constant depending on the operating point. And here I'm showing a simulation run, and this is the midpoint minus V out. This is the voltage across the inductor. In the original version of the video, I just marked here, this one here, while the correct label is, of course, the difference here, it's shown here. So this is the voltage across the inductor. This is the ripple of the inductor, the ripple current, and this is the integral of this voltage, which as you can see is really similar, or in fact it's within a constant of the ripple. And this is because of the following. Starting with Faraday's law, we have Vn dphi to the t, and therefore the flux, the magnetic flux, is the integral of the voltage, while from here we see that B is mu times h, and h is also a function of I, so B is a function of I, so therefore we see that these two are related. So a higher ripple current would mean a higher magnetic losses or core loss. So how can we model the core losses taking into account this behavior? Now these plots are based on the Steinmetz equation. The original Steinmetz equation goes like that. F to the power of 2 and B to the power of 2 times sine k. This is the power loss per volume. Experience has shown that this does not fit well with all magnetic material. So presently what manufacturers are doing, they are fitting data which is measured to this template. In this case we have some alpha, beta, which are different in general from 2. So this is a fitted equation, actually the result of a fitted equation, based on the original template of Steinmetz, except that the power is not 2, but really fitted to the experimental data. So we start with Faraday's law again. We have V is N dphi dt. Then we take out the cross-section area, so it comes out to be N times the area dB dt. Now we can find out what is B, which is the integral of the voltage, times 1 over N, the cross-section area, assuming a sinusoidal excitation, taking the integral, then the phasor, or the AC component of the B, will be proportional to the AC component of the voltage. There is, of course, a phase shift here, which I'm not considering, divided by omega due to the integral, and then this constant here. Or in general, omega is 2 pi f, so you can write it like a constant V over f. So B, in general, AC component, will be the AC component across the inductor divided by f. Now, from here, I'm going to plug in this B into the original Steinmetz equation, here, B squared. So this is now the B. There is a constant here, there's a constant here, so I call it like a K sub 2 times F squared. This is the F squared, okay? So the power, therefore, this F squared and this F squared are canceling out. So the power, therefore, the expected power, according to the Steinmetz equation, is the V squared over 1 over K, which I can represent as a resistor. So therefore, I can say that the power dissipated in the core is equal to the voltage squared on it divided by R, meaning that I can represent it as a resistor across the inductor. So this is actually the very basic classical model of an inductor. We have L, we have the resistance of the winding, and then this is the parallel resistance representing the core losses. Also, I have here the capacitance. This is the interwinding capacitor represented in a lump form. And we understand now that in reality, Rs is a function of frequency because of the proximity at skin effect. Rp is constant only if you assume that the original Steinmetz equation holds, that is the power of 2. And L, in reality, is a function of the current because of the BH curve, and therefore it has to be changed as the DC current is changing. If you assume that all these are constant, then obviously this is not very accurate. In fact, the experimental values of this coefficient, okay, for the Steinmetz approximation or template for practical core, this is for an MPP core, this is iron powder core. You see that the value here of this power terms are around 2 to 1, and C for the frequency, it's again around 1 to 1.5. So if you assume that these are 2 and 2, then this is not very accurate, of course, for a practical core. Same thing goes for a ferrite material. These are ferrite material, and here are the coefficient x and y. This is x and y. These are the power terms here. And we see again that here we are talking about up to 3, the y here for the B, and x is 1.5. These are again experimentally fitted coefficient, which imply that the basic original Steinmetz equation is not very accurate if you take into account practical material. All this goes to say that if I'm assuming a constant value for these components, for the parallel and the serial and the inductor, then obviously this is kind of very limited, and the accuracy really depends on the specific case. Now in simulators like LTSpice, you can actually choose from the library a commercial inductor. So here this 27 microhenry is a commercial inductor. This is by Coilcraft. And here are the value of the parameters here. Now the question is whether the model is exactly as is, or maybe there is an underlying algorithm that takes into account the dependence on the frequency. As we've seen, it's very important for the series resistance, for the winding resistance, and also if there is a deviation from the power of 2 in the Steinmetz equation, this is not correct. Now, if the model is okay, then I can use a very nice tool that they have at LTSpice after running by pointing at the inductor and pressing Alt plus a left click. I can get the product. This is the product, the voltage on the inductors times the current through it, and the average of this thing, and it shows here, is indeed the power dissipated by the inductor. Obviously, it will be correct only if the model is correct, and we are going to test it in a minute. So again, what I have here is this is the midpoint now, this is the ripple, this is the product, so this is supposed to be the power dissipation within the inductor. Now, if I do just a simple RDC type calculation that is taking the average current times the RDC, I'm getting 1.17 watt, while here it shows 1.4, so it's pretty close, which might indicate that the model is really the basic lumped model without any modification. But let's give it a try and test it. So what I did, I used the model as it is, but then broke it into the components. Here I know that this is fixed and nothing will change as the simulation goes on. And here the question that I'm posing is whether somehow the simulator will take into account that there is a frequency dependence. So I ran, first of all, a time domain simulation, and I see that the two are basically the same. Well, there is some difference here, probably due to some numerical inconsistency. And I also ran a AC sweep between 100 kilohertz and 1 megahertz. This is the amplitude, this is the phase, And as you can see, these are right exactly the same. This is one on top of the other. That is the model as it is, and the equivalent network with the fixed component. And then I did a test to see whether the model is capable of taking into account the fact that there is a DC which is changing the inductance. So I've put here a 22 amp DC. This is the operating point. I don't know why this is 22.2. Nonetheless, IL2 has a DC current through it. And when I ran an AC sweep, it's exactly the same as before. So the model does not take into account the DC or the effect of the DC current on the inductance. So the conclusion is that the model that we have here does not take into account the frequency dependence of losses at all. This is a very, very approximate model, and it does not take into account the bias current effect. That is, that the inductor is nonlinear. So this is really very limited. Now, turning to the datasheet, we don't have much information in datasheets about losses. You'll find the inductance, tolerance, RDC, the RMS, saturation current, but doesn't say anything about losses. However, due to the interest in the losses, recently, manufacturer like Coilcraft, and there is another example I'm going to show, is providing a simulation tool that seems to add important information. And in this tool, for example, you start with the topology. In this case, it's a non-synchronous buck converter. You put in the voltage, input, output, current, frequency. This is the voltage drop on the diode. And then it'll give you options for inductors that will do the job for this particular circuit. So there are here different units here. Now, looking at these two, it caught my eyes, and this is something that I've mentioned in the original video, that although the inductance is the same, the current is the same, we see that here the total loss is 2.6 watts. Here it's 0.5. Okay, so this is quite a bit of a difference between these two. Okay, and I wasn't clear what it is, and one of the viewers alerted me to the fact that it says here, for some reason, 14 amp RMS and 5 amp RMS, while in the original request here I've specified 5. So I don't know why it is now all of a sudden 40. But nonetheless, I can choose this and ran a more detailed simulation, which I did. So I've chosen these two. Now this I'll call an X. This is the potted version, and this is the open version. This is probably carbonyl, a iron powdered material, and this is probably a ferrite. I call this X, I call this D. Again, here I see the same thing, which is kind of unexplained. And now I'm getting these plots. So first of all, let's have a look at the ripple that they are showing. This is for the X, okay? And then we have the same thing for the D, and as you'll see, they are the same. Here's the 5 amp, and it goes up to 8, and this is the same thing here. So the ripple is exactly the same. Frequency, of course, is the same, 100 kilohertz. So the two inductors are run under the same condition. Now, it shows here the information about saturation of the inductance. We see that one, which is the D, okay, is saturating very quickly, while the X is saturating slowly. This is the iron powder here, which is kind of typical. But then here, there is something which is very strange, which I cannot explain. and that is the following. The black bar is the losses due to the core and AC losses of the windings, while the gray here is the DC part, that is the DCR, the resistance, the DC resistance. This is for the potted inductor, and this is for the open inductor, and see this huge difference, okay? Here, the AC and core losses are tremendous, while here they are very, both are supposed to be run at 5 amp, and notice that the DC resistance of the D, DC resistance of the D is in fact larger than the DC resistance of the X, while in fact the power dissipation of the D is much smaller than that of the X. Well, I cannot explain this. This is very strange, and it baffles me. There's more information here, and that is the losses as a function of V in. Here we don't see any change, while here it's going up. Again, I cannot explain this. While here, again, we see if the loss is a function of frequency. You would expect, as the frequency goes down, the loss to increase because the ripple will increase. But I see it here, and I don't see it in the D, only in the X. Again, I cannot explain this. So there is a tool, it's working, but I'm really very doubtful about the meaning of these results, and I like to see a comparison between this simulation and actual measurement to see that these are correct. Now, as I've said, other companies are also offering similar tools. One of them is Worth, and by the way, Worth is claiming that they are trimming the simulation model with many or a lot of actual measurements. I don't know, this is what they are claiming. And here again, you input the parameters of the operating point. Again, you see the decrease of L with the current. And by the way, the fact that this is not a very smooth curve might indicate that this is based on actual measurements rather than a approximation. We also see the increase in temperature as a function of the DC. Again, I'm running it for given situation. Again, this is a 50 volt input and 24 output 5 amp. And I've chosen this particular inductor. And here it's broken, the losses are broken down into the AC. This is the total, this is AC, and this is DC. And this is a function of V in, and here the function of the frequency. I see that indeed in the AC component is changed. The DC component is of course not changing with frequency, there's no reason, while the AC component is increasing, as I've said, due to the fact that the ripple is becoming larger and therefore the losses of the core are getting larger. So what are the conclusions of this presentation? First of all, it's very important to realize that the inductor's AC losses could be very significant. This is not something which is small, and if you just rely on RDC and the DC current, you may get big error. And also, SPICE model of inductors are really not sufficient to get us information about losses as a function of frequency. As if we change the frequency, the losses do not change significantly. We don't see the change. And then we see that some vendors provide detailed AC losses through the tools, but the accuracy of the simulator has not been demonstrated to the best of my knowledge. So we have here an open-ended case in which there is a simulator, you get your numbers, but there is no proof that the numbers that you get are really correct when compared to actual experimental data. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.